Hello class, today we're on related rates 4.2 and I thought we'd go over them together. Now these problems that we're going to go over together are very similar to the problems you have on your worksheet. Same scenarios, just different values. I thought that would be a good idea to kind of go over them because all of these are so different, these related rates. And the hardest part, well, the calculus part isn't bad. The hardest part here is just setting everything up and knowing how to set it up. So hopefully this video will help us with that. So the steps I have written here. First step is read the problem carefully and draw a picture if applicable. So sometimes pictures will help. Well, a lot of times pictures will help, but sometimes we won't really need pictures. Step 2, identify the variables and rates of change. So we need to label the variables. It'll help keep everything together and orderly. And then step 3, we need to write an equation that relates the variables. And sometimes we may need more than one equation. That's not the case for any of these today. We'll only have one equation today. And sometimes I tend to switch steps 2 and 3. Sometimes I'll come up with the equation first and then I'll identify the variables. So you can switch these if you'd like. And then step 4, implicitly differentiate both sides of the equation. So this is just implicit differentiation. And then step 5, substitute variables and solve for the unknown rate. So let's get into this. The first example, water leaking onto a floor forms a circular puddle. The radius of the puddle increases at a rate of 2 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? So we have this puddle here, and the radius is increasing at 2 centimeters per minute. So it's maybe like a slow leak that forms a puddle. And we want to know how fast is the area of the pool increasing when the radius is at 5 centimeters. So let's I guess start off with step 2. We need to identify the variables and rates of change. So let's see. Well, we have well, first we're looking for area. Well, we're looking for the rate of change of the area, but we will have an area in here. We also have a radius, and that will be r. And of course, it's not in there, but the point of these related rates is we always have that time factor in there. So we'll have time as well. Now, what we're looking for is the rate of change of the area, so we will have a dA dt, so that's the area, the change the area with respect to time. And this is the rate of change of area. And then we'll also have a rate of change of the radius because the radius is changing as well. So that's going to be dr dt, the change in the radius in respect to time. So that would be the, and you know, I'm going to shorten this. I'm going to write ROC for rate of change of radius, and that equals 2. And what are we looking for? We actually want to find d of a, or dA dt, because that is dA dt is the rate of change of the area. We want to know how fast is the area of the pool increasing. So we want to find, I'll change colors here, find dA dt when the radius is 5, when r is 5. So I just write this line. It just tells me you can think of it like as when. So find d of dA dt when r is 5. Okay. So I won't really draw a picture on this one, but let's see. What is the area of a circle? The area of a circle is a equals pi r squared. So that's the equation we're going to use. It relates our area and radius together. Time is in there, but it's the derivative. It's in the derivative. So cool. So we did step 2, identify the variables and rates of change. And then step 3, we wrote the equation that relates the variables. And in this case, and all of these cases we'll do today, we'll only need one. And then step 4, implicitly differentiate both sides of the equation. So I'm going to find d dt, and so I'm getting the derivative in terms of time. And so I'm multiplying both sides by d dt. Or rather, you could think I'm taking the derivative of both sides in respect to time. So d dt of a, well, a is just a variable, so a is just, what's the derivative of a? It would just be 1, right? And then we need our dA dt. So the derivative of a is just dA dt. Equals, now pi is a constant, so we don't need to take the derivative of that. Well, we can just write it out front. And then we want to take the derivative of r squared. So we're taking derivative of the variables here. So the derivative of r squared is 2r. And then we need our dr dt. So here we have it. Here is our function that we took the derivative of implicitly. And if you need more help with the implicit, I would just go back and look at the implicit differentiation video we had and look at that. So dA dt is equal to pi 2r dr dt. Now, what are we looking for? We want to find dA dt. So it's already solved for us. dA dt is already solved. We just need to plug in the values. Excuse me. So let's see here. dA dt is equal to pi 2r. Now, r, we want to find out the dA dt when r is what? When r is 5. So I'm going to plug in 5. And then dr dt. What is dr dt? dr dt we defined as 2. So dA dt is equal to, we have pi, so let's multiply all these others together. 2 times 5 is 10, times 2 is 20, so 20 pi. And 20 pi what? Well, we're talking about area, right? And we're talking about centimeters per minute. So how fast is the area of the pool increasing? 20 pi centimeters squared per minute. And that's it. So again, what we did was first we read the problem, right? And then step 2, we identified the variables and rates of change here and what we're looking for. And then step 3, we found the equation that relates all of our variables. Step 4, we took the derivative implicitly. And then step 5, we plugged in our values that were given. And we're done. So let's take a look at some others. Oil spilling from a ruptured tanker spreads in a circle on the surface of the ocean. The area of the spill increases at a rate of 3 pi meters squared per minute. How fast is the radius of the spill increasing when the radius is 10 meters? So here, the area is increasing at a constant rate, and the radius is then increasing at a differing rate. So let's again define our variables. So we're still talking about a circle here, right? It spreads in a circle. So we have an area. We have a radius. And we have time, of course. Let's see. The area, we're given the rate of change of the area. So that would be dA dt. And let's see, that is the rate of change of area. And that is given as 3 pi. I guess meters squared per minute. Okay. And then how fast is the radius changing? or increasing. So that's going to be our dr dt. So that's our rate of change of radius. And what are we finding? We're finding our dr dt. So we want to find dr dt when the radius is 10. So when r is 10. So now we can get our equation here. It's just the area of a circle again. So A is equal to, let's see, pi r squared. And now we want to differentiate this. So let's take it. We want to take ddt of both sides. So we're differentiating it with respect to time. Because we want to know the rate of change in terms of time. So d dt times a, well, the derivative is just going to be dA dt equals, pi is a constant, so again that just goes right out front. We don't do anything with that. And then we have r squared. So take the derivative of r squared. That's going to be, just using the power rule, that's going to become 2r to the first power, right? We don't need to write first power. And then dr dt. So, now that we've differentiated, what are we solving for? We want to find dr dt. So let's get dr dt by itself. Or, well, we can plug in our values first if you'd like. How about we do that? Yeah, let's plug in our values. So we're given that dA dt is 3 pi. So I can substitute, I can plug in 3 pi in for dA dt. Equals, and I'm just going to rewrite this as 2 pi. Times our r, we want to know the dr dt when r is 10. So r is 10, and then dr dt. Okay, so let's see, let's simplify this. 2 pi times 10 we can write as 20 pi, so 3 pi equals 20 pi dr dt. And then what do we want to do to solve for dr dt? Well, it's being multiplied by 20 pi, so let's divide both sides by 20 pi. Oh, this isn't 30, it's 3 pi. That was my bad. Okay, that's 3 pi. Okay, divided by 20 pi. So this all cancels, and these pi's cancel here. So we're left with 3 over 20 is equal to dr dt. And that's it. 320 what, though? That's going to be just the, how fast is the radius? So centimeters per, what were we in? Oh, meters, oh, oil tanker. Meters per minute. So this is, I'll write it with the units on it. 320 meters per minute, and it's the radius, so we don't need to do meters squared. It's just the radius, so that's just the length in 1D. Awesome. Okay, now we have the conical paper cup problem. So a conical paper cup is 8 centimeters tall with a radius of 8 centimeters. The cup is being filled with water so that the water level rises at a rate of 3 centimeters per second. At what rate is water being poured into the cup when the water level is 6 centimeters? So, we have, let's see. Well, now we're dealing with volume, right? Before we were dealing with area, so now we have V is our volume. We have a radius, right? It's a conical paper cup, so we will have a radius. We will have height. So we have a radius, and then we have an 8 centimeter tall, so that's going to be height. And then we have T for time. All right. Now let's talk about our derivatives. What are our rate of changes here? Well, let's see here. We have dH dt, because it's the rate of change the rate of change of the water. or of the height rather. So rate of change of height of water. And that is given as 3. The cup is being filled with water so that the water level rises at a rate of 3 centimeters per second. So that's going to be 3. And then at what rate is the water being poured into the cup when the water level is 6 centimeters? So that's going to be a dV dt. So dV, that's going to be the volume with respect to time. So dV dt is equal to, well, that's the rate of change of volume. And so that's actually what we want to find. We want to find at what rate is the water being poured into the cup. What is the rate of the volume of the water? So we want to find dV dt when the water level is 6 centimeters. So when the height is 6. Okay. So now we need to come up with an equation. Well, this is a conical paper cup, so the volume of a cone, if you've forgotten, is V is equal to 1/3, and you can see this written many different ways, but pi r squared h. Now, this is a nice problem for us, and that is this. Notice that notice that the paper cup, let me draw a picture here. Notice that the radius of the paper cup is the same as the height. And I didn't draw this to scale, but the paper cup is 8 centimeters tall, and the radius is 8 centimeters. So we can actually simplify this this equation here. Since r is the same as h, wasn't r squared times h, wouldn't that be the same as just writing h cubed if they're the same length? And yes, it is. So I can rewrite this as v is equal to 1/3 pi h cubed, since r and h are the same. The only reason I could do that is because r and h are the same. If they were different, we'd have to use a different method, or we would have to find out how to put h or r in terms of h. So, okay. Now let's take the derivative of both sides now that we have our equation. So d dt, do it in terms of time. So d dt times v is the derivative of v is just going to be dv dt, which is nice. And then this 1/3 pi, these are constants, so we don't need to take the derivative of those. We can just write those out front. And then take the derivative of h cubed, since that's a variable. So that's going to be 3h squared, just using the power rule. And then, of course, we need our dh dt. Okay. We can simplify this a little bit. This actually cleans up pretty nicely. This 1/3 and this 3 cancel, right? 3 times 1/3 is just 1. So let's go ahead and rewrite this and make it look a little nicer. So this is now pi h squared dh dt. Okay. So let's now plug in our, well, first, what are we solving for? We want to find dv dt. Okay, so it's already simplified, or it's already solved for us. So let's just plug in our values. We have dh dt is equal to 3. It's the rate of the water. I guess it's centimeters per second. That's probably, it's the change in the height of the water. And let's see. H is given as 6. We want to know when the height is 6. So dv dt is equal to pi times h squared, so 6 squared, times dh dt, which is 3. And multiplying these together, we get dv dt is equal to 6 squared is 36. 36 times 3 is, oh boy, 108. Let me double check. Yep, 108. So this is 108 pi. And our units, well, this is what is the rate of the water being poured in the cup when the water level, so what is the rate of the water? So this is going to be cubed here. So this is going to be centimeters cubed per second. So 108 pi centimeters cubed per second is the rate at which the water is flowing in. Okay. We have two more examples that we'll go through. A spherical balloon is inflated so that its radius increases at a rate of 3 centimeters per second. How fast is the volume of the balloon increasing when the radius is 4 centimeters? So, let's see. Well, maybe this time we'll start with the formula. It's a sphere. So the formula for a sphere, if you've forgotten, is 4 over 3 pi r cubed. So what are our variables here? Well, we have V. V is our volume. We have R, which is our radius. And we have T, which is our time. Okay. And then we have dr dt. Let's see. The radius increases, so that's going to be dr dt. Is the rate of change of radius, which is equal to 3 centimeters per second. That's how fast the radius is increasing of the balloon. And we're also going to have dv dt. That's what we're looking for. Because we want to know how fast is the volume of the balloon increasing. So dv dt is the rate of change of volume, and that's what we're finding. Find dv dt when the radius is 4, when r is 4. Okay, so we came up with our equation. We have our variables labeled and our rates of change labeled. Excuse me. So let's go ahead and take the derivative of this. So ddt, ddt. So ddt of v is dv dt is equal to 4 over 3 pi. Those are constants, so we don't take the derivative of those, right? Just take the derivative of variables. R cubed, so that's going to be 3r squared, right? Just using the power rule. And then we need our dr dt. And this cleans up very nicely as well. This 3 would cancel with this 3. So let's go ahead and rewrite it. dv dt is equal to 4 pi r squared dr dt. Okay, so let's see. We took the derivative, so now we just need to plug in our values and we should be good. We are solving for dv dt, so that's already solved for. So that's good news. So let's see. We have dv dt is equal to 4 pi r squared, so we want to know when r is 4, so it's going to be 4 squared times dr dt, which is 3. And if we were to multiply all this out, 4 squared is 16, 16 times 4 is 64, 64 times 3 is 192. So we have 192 pi. And this is volume, so it's going to be centimeters cubed per second. Just like that. Okay. So that is how fast the volume of the balloon is increasing when the radius is at 4 centimeters. 192 pi cubic meters per second. Okay. So finally, last one. Sorry this is such a long video, but these things are tricky. These things can be tricky, and they're all a little different. So this example, an observer stands 800 feet away from a launch pad to observe a rocket launch. The rocket blasts off and maintains a velocity of 700 feet per second. Assume the scenario can be modeled by a right triangle. How fast is the observer to rocket distance changing when the rocket is 2,000 feet from the ground? So rockets, as you know, when they take off, they're not at a constant speed. This says it's at a constant speed. So let's just assume we have a rocket which takes off at a constant speed. Maybe one of those ones with the air that's filled with the air that you kick the thing on the ground and they go off. I don't know. Anyway, so here, let's draw a picture. I always tend to draw pictures, especially when it comes to triangles. So here we have the rocket. The rocket is taking off here. I'll draw a poorly done rocket. Looks like an arrow. And then we have the observer standing, and they're 800 feet away from each other. And let's see. We have, I can call this the height, and then this we'll just call x. Okay, because that's what we're looking for. So how fast is the observer to rocket distance changing when the rocket is 2,000 feet from the ground? So we want to. So what we're really looking for is dx dt in this case, the rate of change of this x value. So let's see. X is the observer to rocket distance. H is the height. And of course we have time. And we're going to have, let's see, we're going to have, well, what are we given? We're given the rocket blasts off and maintains a velocity of 700 feet per second. So that's going to be dh dt. That is the rate of change of the height, isn't it? So we have dh dt, and that is the rate of change of height of rocket. And we're given that to be 700 feet per second. Okay. And then dx dt is the rate of change of observer to rocket distance. And that's what we're looking for. So we want to find dx dt when the height is 2,000 feet. So when the height is 2,000. So we're going to be dealing with a lot of zeros here, I imagine. Okay. So now we want to create an equation that relates all of our variables, our x and our h. Well, we're dealing with a right triangle. So what equation do we use when we are dealing with right triangles and the side lengths of right triangles? You may have guessed it, Pythagorean theorem, where it states a squared plus b squared equals c squared, where c is the hypotenuse. So I can rewrite this, I can write it in terms of 800, h, and x. So I can say 800 squared plus h squared is equal to x squared. So now that we have our equation, we can go ahead and take the derivative of this. Now, what is the derivative of 800? Well, let me write d dt first. Both sides. That d dt. Okay. So let's take the derivative. What is the derivative of a constant term? In this case, this constant term is 800 squared, which is 64,000. But that just goes to 0, doesn't it? It goes away because, you know, the derivative of constant is 0. So we're dealing with now the derivative of h squared. Well, that's going to be 2h and then dh dt. And then derivative of x squared, that's going to be 2x dx dt. And what are we solving for here? We're solving for dx dt. So let's go ahead and solve for dx dt. So we can take we can divide both sides by 2x. That cancels, which is what we want. I'm just going to turn this thing around. I'm going to write dx dt out front. And let's see what happens here. Oh, this cancels. That's nice. So we have h over x dh dt. Okay. So let's see. We're looking for dx dt. We have h over x times dh dt. And look what we're given. We're given dh dt. That's 700 feet per second. So I can plug that in. I'm given the h at 2,000, so I could plug that in. What about our x? We're not given an x value, are we, to plug in? So that creates a problem for us. But we can use, again, Pythagorean's theorem to figure out what x is equal to. Well, think about this. This is 800. We know that. When the height is 2,000, what is the x distance? So, down here, I'll just redraw the triangle. We have 800. This height is 2,000. And this is what we're solving for. We need to know what the x value is at that point. We're not given it. So, this is going to be a lot of zeros. I'm just going to plug into the calculator. So we're going to have 800 squared plus 2,000 squared equals, what is that? 4,640,000. And then we take the square root of it, don't we? And we get 2,154. I'm just going to call it an e. I'm just going to round it off even. It's pretty close to it. So x is equal to 2154. So now we have all the information we need in order to do this. So dx dt is equal to h, which is 2,000, over x, which is 2154, times dh dt, which is given to us 700 feet per second. So we multiply all these together. Again, I'll put in the calculator. Let's see, 2,000 divided by 2154 times 700. And we get 649.95. I'll just round it to 650. So dx dt is equal to 650, and what are we talking about? We're talking about distance. So distance is just the first power, right? It's not squared, or squared is area, cubed is volume, and we're dealing with feet per second. So 650 feet per second is the rate at which the rocket is. Well, the rate at which the rocket is getting further from the observer. So, sorry about such a long video, but that's all I have for y'all today. So get started on the worksheet. Let me know if you have any questions.